Hey, Boone, how are you?
Oh, dude, I'm good.
Um, about some of the work, the white papers that we were talking about, I'm busy this week, but next week we'll start working on it.
Okay,
And
okay.
we'll,
Hello?
yep, I'm here.
Okay,
Let's,
it's actually my connection had issue. I'm
no,
trying to
no,
fix that. Yeah.
no, just went quiet. Let's see. Let's see how many people will join us.
Okay.
Hi, Victor.
Hey, good morning. Oh, afternoon.
How are you? Um, where, are you joining us for the first time?
I've joined a couple ODSA call lately. Mainly interest. I'm just mainly here as a listener.
Oh, okay. Okay. What is your interest in chiplets? Are you looking into chiplets, designing chiplets?
Um, yeah. So really I'm interested in the overall chip and chip design. Yeah, I understand what ODSA is about, the packaging of it.
Okay. Yeah. Okay. Which company do you represent?
I'm independent.
Okay. I see. All right. Well, welcome to CDX then.
Thank you.
So today, hey, Produce is here.
Hey, David.
Hey, Produce, how are you?
I'm good. Tony may not be able to join today.
Okay,
He's trying.
okay. So let's get started and see how much we can accomplish. Today was supposed to be a PI-SA meeting. And does any of you work on PI, power integrity?
In what way?
From outside of chiplet point of view.
I mean, I work in these things from a what can I simulate perspective.
Okay, yeah.
So works as well outside the chip as inside the chip.
Yeah. Boone, how about you?
You mean the sub? My focus is mainly within the die itself, so including some of those convergence and so on, the methodology how to do it. That is where I'm in for the power as well as the SI related,
Okay.
and including the liabilities are not above the die.
Okay. Okay. So even that's good. So when you're analyzing let's talk about power integrity, okay, for a moment. When analyzing the power integrity of a die, you somebody would make an assumption about what is outside the die, right? Or conversely, say somebody has a chiplet and they will specify requirements for the power supplies, the package inductance, package capacitance, and so on, right? I wanted to capture these in CDX ML. So I'm not entirely sure where to start from. Here's a couple of things I'm thinking of, okay? One is
I think with chiplets is optimizing the power delivery. And I was working at Cirrus Logic on switch cap power stuff, and we had a guy do a talk for the IEEE, and he was saying that switch cap stuff's only efficient over a narrow range, so you're kind of wanting to sort of tailor it to what you're doing. So you want to get the information about the sort of capacitive loads and ranges of the chips so that you can design the switch cap stuff to match.
okay. That's a very good point. Okay, so okay.
I mean,
So
one of the reasons there is and it might be just picking one of the right chip off a pile for the job, because
okay.
you're probably going to have a range of them on like 65
Yeah.
nanometer. They're really small things. You'd probably have them on 65 nanometer.
Yeah. Okay. That's a very good point. So the first thing that comes to mind that's in any reasonable data sheet would be the load currents and release currents, both ways, right? That has to
Yes.
be provided per supply.
Yeah.
Right.
There was a thing I think we did a while back. It said, I'd like to know the modes that a chip works in. So if you had a list of modes and what the voltages and currents corresponding to those are, it would be good. And the sort of percentage of time you spend in a particular mode. So basically, when you're looking at a system of chiplets, you want to say, okay,
Yes.
here's a bunch of valid modes for the whole system, and what the submodes of the individual chips are, and then you can kind of do all the power modeling stuff.
Okay. Yeah, modes are already in IEEE 2416. It has a definition of mode, but we can talk about this. Okay. Let's actually CDX ML already has a notion of a mode, I believe, so we can use that as well. Okay. Um,
I think the other thing was mode transitions. Which mode transitions can you do?
modes. Okay.
So the power state's kind of like a big state machine. It should only go from like one state to another. Like
Yes.
you probably don't want to see everything on at the same time. You know, it's like,
Yeah, that's right. Okay. Um, how about the capacitance on chip? Is that necessary to do outside simulation of the power of PDN?
I think
Oh,
you need the capacitance is if you want to get the total power and so on, right? But the for the PDN you actually need the caps values on those the cap values on those power mass as well.
yeah, I think you need that, and then you need to know what the ripple tolerance is. You know, the noise tolerance on the power line.
okay.
Because, I mean, a lot of people are trying to do DVFS these days,
Yes.
so you kind of want to
So,
know, kind of,
so
you know,
this,
swing
yeah,
the
this,
voltage quickly or not.
yes. So this will be what the chiplet requires in terms of uh, supply, ripple, and noise, right?
Yeah, there was somebody who did a RISC-V chip where they just pumped the voltage up and then let it sink while the chip was working for a while, and they would just pump it up every so often to keep things going at the speed they wanted on average.
Mm-hmm. Yeah. Okay. So like with a charge pump or what?
There's probably some PWM kind of inductive
Okay.
thing. I don't know what they were doing exactly, but definitely kind of like a charge pump.
Yeah.
I mean, it's the sort of thing you want to do is you have something where you've got like an inductor carrying current, and then you go around injecting current into the caps where you need it to keep the voltages
Yeah.
up.
Yeah.
The thing with the RISC-V processor is it's not particularly sensitive to the noise on the power rails when it's low frequency noise.
Yes.
But you did need to, for that one, you did need to change the frequency of the clocks to match the voltage you had. So it would start off
Yeah.
fast, and then it would get
Yeah.
slower
Yeah.
as the voltage dropped, and then you bump it up to keep the average processing
Okay.
speed you needed.
Okay.
Um,
I see.
so there's a bunch
So
of
that's better.
information in there about like, you know, what kind of ops rate you've got versus what voltage.
Yeah.
And what the minimum
Okay.
system requires.
Um, okay. How about any requirements for external chiplet external capacitance and loop inductance? Is this typically required? I mean, would a chiplet require certain values for those? Or this is up to the package designer to figure that part out?
There's a whole thing in like analog tests that came up that nobody's doing, which is like back annotating what's actually there in the way of wiring capacitance. So the chips the kind of thing you're wanting to do is design a system with all the chips, and then when you come to lay them out, make sure that you've got the right tracks there that have the right inductance and capacitance for the whole thing to work. But you kind of need to back annotate from the design tool for the layout into simulation tools to see if it's working the right way.
Okay. And
So
what do you back annotate?
and chips at SPEF.
Okay.
So,
But
I think
if
SPEF works for most things.
oh
It's just Spice netless, really.
yeah. How about if we're talking about chiplets, do you back annotate something onto the package, or for the chiplets itself, you back annotate, I don't know, what the capacitance is, inductance is, things like that?
I mean,
Or
you're in IBIS land for this stuff, for the packaging, for the chips themselves.
I'm sorry, say that again. I missed it.
IBIS is the standard for doing pads.
Okay, but how about that would be for signals. How about for power?
I'm not sure what you can actually do in IBIS completely. I mean, trying to kill the thing off for years, but nobody's nobody's helping.
Yeah.
This is
Okay.
typically modeling the IOs data.
I'm sorry. Say that again, Boone.
This is usually we use it to model the I/O signal integrity.
Yeah, IBIS. Yeah.
In theory, you should be able to translate things like IBIS into behavioral modeling languages like Verilog EMS that are more extensible. I'm not sure if anybody's really trying to do that. So I put a couple of links in the chat. One of the things I came across at Semicon was somebody gluing chips down, where they were using epoxy with, I think, iron filings in it. And if you stuck it in a magnetic field, you would get these vertical wires in the glue, and they would connect your chip for you. And something like that is not going to be as good a contact as a solder bump, but a lot easier to assemble in some ways.
Yeah.
So you've got things like the contact resistance for different methods, as well coming into this.
You can tell. Okay.
So there's also people doing like power on the backside of chips.
Yeah.
So you're
I haven't
using
read. Somebody's doing actually not only power. There's other routings on the power on the backside.
yeah, it's like 4 layers of wiring in the one I saw online. Yeah. But if you're doing that, you're probably doing wire bonding for the power, where you're doing something like the glue stuff for the signals.
I think we also need those waveform profile as well for the supply that's expected, right? The worst case.
The other link I put in the chat is for guys who'll print the wires for you.
Yeah.
Then the nanojet. How thick do you need your wire? Just layer it up.
Boon, what were you saying about worst case?
We need those worst case waveform profile, right? Where those those DC plus ACs for those die. The waveform, the dynamic waveform, the worst case one. That was will show the group effect and so on. The waveform transition over the time a dynamic sample that we send it.
Okay. So let's talk about that for a moment. So okay. Worst case current, right? You need that to do airdrop and things like that. You need long-term current.
Supplies is the current is the earlier on we actually mentioned there's a release currents per supply, right? But then you also need to have the waveforms the worst case waveforms observed, right? So that is where we do those simulation that we know already.
Yeah. How do you define a worst case waveform?
Dynamic waveforms the dynamics voltage drops the dynamics voltage on the dies for supply, right?
I mean, is it worst, right? When I think of a waveform, I can think of several different worst cases, right? One is you want the highest current so that you can check your PDN for airdrop. One is you want the highest load ramp and the highest load release, right? And then you may want the fastest current ramp and ramp up.
There's a max power. Typically, the waveform drop should be the highest current, meaning that it will be also the max power scenario, right?
Okay.
Max power, then you see how those at the dynamic situations, and then it will be the voltage waveforms will also reflect the truth as well.
Okay. So the maximum power scenario current waveform.
Voltage waveform.
Okay.
Yes.
Voltage or current waveform? It should be current, right?
Yeah, you have the currents, and the current string will be one direction, and then voltage will be another. Then you are going to target the power, and then with the voltage you actually can have those CDIs, effective CDIs observed or that representing the die effect, right?
Okay. Okay. So current and voltage waveforms, effective C die. And effective
The effective CDIs actually can derive from there from the above information.
oh, okay, yeah, actually you're right. Okay. So if somebody was to give me only the load release, the load ramp and C die, I can derive voltage from there then, right?
Yeah.
Okay. So there's a little bit of mutual exclusive, I mean, of our definition, right? If somebody provides all three, let me take a note about this. Okay. Yeah, this is good.
And the other thing maybe is that if this is considering is actually the information is actually capture from let's say typical scenario, right? Typical corner scenario. Then if you want to do the estimation by swinging let's say to the fast corner, which is the worst case, then I guess the extra information that we need to perform the power integrity will be the the delta V means that should be applied, and then that actually translate to some slopes the if they have those sloping the slope curve that exist by sigma, then we can actually use it to use a formula to calculate to based on the TT corner information, then interpolate it into those let's say fast corners, the droops and so on effect behavior. Assuming the information that we get is actually the TT, then how do we want to have the ability to interpret the fast corners behavior estimation scenario? Then we may need that kind of information. Typically, it's determined by the C die. The V means the per sigma and so on. That is and then the slope information, so that we can calculate I think it's a log effects of behavior. That's then only we can calculate it.
Okay.
Right. So that information, if it's given, that would be nice, but it may be a bit tough. So maybe we want to have it something like estimation, or if it's directly the delta, we mean that will be a bit gross. Right.
Okay, I think this went a little bit over my head. Yeah.
I mean, the scenario that let's say if the information that we have, the worst case is actually at the TT, right? Then the droop may be even worse. It is a fast corner power supplies and those device corner scenario as well, right? So whether we would like it to be able to interpret based on those TTs to those fast corner, that is a scenario, but maybe not for initial phase, I guess.
Yeah. Okay. Okay. So that can be okay. Okay, I understand what you're saying now. Basically, what we want is information for different process corners, right? TT and FF, since it is not known which one may produce worse results, correct? Did I capture this one right?
Yeah, something like that. So that information is either you provide it individually, the stating this is actually related to the TT process. Then so if you want to have it explicitly for the fast process, then they have to re-extract and then apply the same information again, right? Or the other way is that if they can share the expected the slopes information for the per sigma change of the VT corner that can and then the exactly the delta value, then we actually can use it to with the CDX information we can use it to estimate the total powers scaling effect, and then the potentially the waveform behavior, and also those
Okay.
yeah. So that is one way or the other. If it's go by individual, then okay, or you want to have it extra information so that we can have scaling. So that's the other approach.
Okay, so if I understood you correctly, what you're saying is provide di dt change over a process sigma variation to allow.
V means that's a V mean that we need to know. Yeah.
Okay. Sorry. This Vmin or
it's a V mean, right? Because there's a typical corner V mean and also the fast corner V mean is different. There's a slope that we have, and also the delta V mean.
Okay. Interpolation. Okay. We also want the Vmin at the different corners, right?
Yeah.
Okay.
You go by per sigma. Yes.
Okay, so I think if I remember from CDK, what we said is that vendor needs to provide CPM, right? And with this CPM, we can do the simulation. If they have them at different corners, even better. But if we know what the targets are for Vmin for a given waveform, right? Okay, CPM will have the waveform. That's one way, and it will have CDI. But then the Vmin is not in there, right? Because this is a target, right? So if I think about it, so this will be CPM, right? And this will be CPM because the CDI will be somewhere in the CPM.
Yeah, this one will be stick to those per process. So you don't have the information to scale from one process to the one process many TTTs to fast scenario. So yes.
Okay. Yeah. Okay. So CPM here, what we're saying is CPM may be needed per corner for better analysis, right? Because we don't know which one is the worst case CPM.
Yeah.
Okay.
whether you want to add additional information so that you can have a scalar based on those for the existing CPM that you have, or you want to provide per corner. Yes, correct.
Okay. Good. But the Vmin is not in CPM. So we can, that will, okay, we need to capture. How is Vmin related to supply, to tolerances for the supply in terms of ripple and noise?
So the Vmin, right, it's just like those threshold voltage behavior, right? So if you have those the die at the TT corners and then with different thresholds transistor inside there, right? So if the typically the TT corners silicons has because of has its own Vmin. Let's say it's maybe it's 1.0, right? But the fast corners are supposed to be have those V means that less than 1.0 because the device are supposed to be faster and then also there's more power consumption. But then
Yes.
the one that is coming from the social corners that the V means are supposed to be higher than 1.0. So that is how it actually behavior. So the slope will be slightly a negative slope, but the CDX behaviors are for the inverse case, right? Fast corners should be at the upper value, and then compared to the TT corner, but then the social ones should be at the lower value compared to TT corner. That is a typical curve that we're going to have. Though that is not straight, but it's in the some logs of behavior. Right. So usually people estimate with the some exponential calculations to derive that output, right? To estimate, yeah.
Okay. I think I understand. Okay. What else is there for power supplies, power integrity that a vendor needs to describe about its chiplet, and B, in terms of having a specification about what the external power supplies need to meet, right? We talked about worst case current. This is information. Okay, let me then split these into two more. In the data from vendor, data about chiplet from vendor. Okay, and then the other group would be target requirements, limits for external power supplies. Okay, then these two will go in this section here.
You chuck thermal derating in somewhere.
I'm sorry, say that again.
Can you throw thermal derating in there somewhere?
Yeah, the also important for the distributions budget as well, the thermal distributions and so on.
What do you mean by thermal derating and thermal dissipation?
Usually your speed of a digital chip will drop off as it gets hotter. So you got a maximum performance for any given temperature.
Okay.
The lifetime comes down as well. So there's like, you've got a mean time to failure at a given temperature sort of thing. And
okay. So as a say I'm getting a chiplet from a vendor. what do you do with the term of the derating information?
Well, it's going to sort of give you an idea. If you're trying to balance up mean time to failure across all your chips, you know, some of them might run hot, some of them might not like running hot to get the lifetime you want, depending on what they're doing.
Okay, but then each chip is going to have its own maximum temperature, right? Specified that
So
this
it-
might
I
maximum.
think
it's going to work
you-
less well towards that temperature. Eventually, it'll just fail in a really short time and it's running too hot. So it's mostly electromigration problems. So given that you're stressing it, it won't last as long if you heat it up.
I think you also need the actual temperature where this information is captured, right? And then
So
with that temperature, and so you have the thermal and also the thermal thermals.
It might
and then the
drive a
power
trade-off. It might drive a trade-off like using a SiC or a GaN chip versus a silicon chip for something, because they can take higher temperature. So to drive some of the powered IC decisions.
But okay, I still don't
If a
get that,
system
right?
is if a system is
Uh,
working, it's going to fail with electromigration at some point.
Yeah, but what
That's just how they fail.
when a chiplet is signed off, it's signed off at a given maximum operating temperature, and it's signed off for a given lifetime. Say it's 7 years, right? So
Yeah.
I know that when I get a chiplet that's signed off within that, I know it has been signed off to that, and accordingly, my system will be with 7 years of a life,
Yeah.
right?
Yeah,
So
I think Intel designed for 8 years is the stuff they do. But you know, you can push it over that limit, and it would be good to know if you pushed it over how long it's going to last. Sort of data.
so you're saying if you use the part above its maximum temperature rating, how long it will last?
Yeah. I mean, it's one of those things where you get mil spec chips, you get regular spec chips. And, you know, the guys who build the chips probably have the data on how long it's going to last at any given temperature. You know, so if you can pull that in, then you can use it to sort of balance up other things on your chiplet system, because you kind of want
Isn't
all
that
to fail at the same rate.
isn't that a straightforward estimation anyway, right? I think it's an exponential formula that if you sign off right to this temperature and this lifetime, you can back calculate from that, given a different temperature, what its
I'm just
lifetime
saying
is going to be.
it might be useful information to have if you can get it, rather than just this chip only works up to 125, you know, or something.
Okay.
Um, I do agree that you need to also have those temperature information so where this is captured, right? And then with those dice coefficients where you can translate these are thermal budgets, and then with those how much is potentially is the ability to dissipate the thermal. And if you, because each time may be from a different process, right? And then you really don't want to have one dice really at a really tough to dissipate because of those technology used, and then the other one, and then at the application level, how you go to resolve the CTE effect as well, right? Beside the dissipation.
Okay, yeah. So if we're talking about CTE,
Yes. And also
that
the temperature that ones, because how it achieves let's say it's power ups are higher, and there's ability to dissipate for die 1 and die 2 will not be same, right? And the translation of the temperature raise from die 1 and die 2 will not be same. And then how do we have the information that estimate this the temperature itself if it's under the same package, right? That will be some proprietary information from the foundry that's needed as well for that technology.
okay. So again, let's think about the CDK. What's in the CDK today, right? In CDK, if for a given triplet, we are going to get, at least we are asking people provide ECXML. ECXML contains materials and contains geometries, right? With that information, it doesn't, actually today it doesn't capture mechanical information like CTE, but that's that property specifically is being captured in the material design kit, right? So technically, the way I'm thinking is, right, you got a chiplet with geometries, and you got the MDK material design kit that is related to this chiplet. You can do, and then adding power power model to it, you can do mechanical simulation with thermal and mechanical, right?
Correct, but the information, the temperature for this power integrity, the sound capture the temperature, so you at least need to have an inference of where, yeah, what's the temperature that's used to generate this information at this moment, right? In the power integrity.
Okay. I see what you're saying. Okay. Okay. Let me. I understand what you're saying, and let me continue reworking this, and I'll add it here. Actually. Okay. Was women a target that the customer needs to meet, that right? We just talked about it. Okay. All right.
Women
Let's
is
do.
effective. Yeah.
All right. Okay. Now, we just talked about that's what you mean, right?
Yes.
Okay. So now, Kevin, about MTBF. Let me think about this. This I'll put in a different place, which will be, where do we capture the rating? The rating, right?
Yeah. It's kind of a DFX thing. Where you're looking at how your system's going to yield and fail and use.
Okay, so I'm calling it a designed lifetime of a chiplet, right? Because each chiplet is designed with an expected lifetime, right? Whether it's 5 years, 7 years, 10 years,
Yeah,
80
so
years.
you can do it that way and then add a D rating on top.
Yeah. I think, let me check on this one.
Yeah, it's partially to get people to think about the problem, and then like, if it's an advantage to them supplying the data, they will.
Yeah. I think
I
there's
think this one is a bit tough because that's actually involve the tolerance, and then lifespan of the year is a DPM part of the thing, and I don't think I see any formula that actually are going to be able to use and able to provide from the foundry, unless they tell you there's some information just like the house, budgets can be relaxed per lifespan. So let's say if it's 10 years, this is a tolerance value. If it's 6 years, this is a tolerance profiles value that's given by the country. But at this moment, I don't see something linear formulas that's given, but it's more like a by year, and then this is a short tolerance that's if it's a shorter lifespan, this is straight higher tolerance that it can absorb. But I'm not aware how they actually come up with these tolerance by years in the background. So unless someone can tell, that would be nice. But at my level is I can only see by lifetimes there's a projected the fixed one. This is the extra tolerance that you can have, or lesser, something like that. Yeah.
I think I have a vague memory, maybe 15 years ago, seeing a formula that was saying, "Hey, here's the formula about right how your limits will change if you change your expected lifetime." I need to do a little bit of research whether that was a Foundry given formula or whether it's a standard formula, right? That you can use to, if you know your chiplet and you know approximately what kind of process it is, you can derive the expected lifetime variation. And it was actually exponential formula, right? The Hopper,
they're all nasty exponentials of these,
right?
Gaussian distributions.
Let me do a little bit of research on that one. Okay. Yeah, let's talk about that discussion for time being, because I'm not sure how this fits into the power integrity aspect of it, right? Here we are talking about the reliability aspect, which I think falls into a slightly different category in CDXML. But this is an interesting question that I need to think about and do a little bit of research on that. And if you guys want to take a look and do some research as well, I think that would be awesome. And let's talk about how do we capture this information. Because here it gets a little bit easier, right? If it was a packaged chip, right, with a substrate and BGAs and chip and say mold on top and things like that, probably estimating the lifetime variation of that part with temperature would be very hard, right? Because we have so many different materials, different cities, different life expectancies. But here we're talking about a chiplet, right? Which is fairly standard with copper wires, right? And copper kind of behaves approximately the same, maybe? I don't know. Yeah, let me take a look at that.
So actually have some relationship with the dielectrics and also the process recipes as per my understanding.
Yeah.
Somebody was doing an interesting process where they deposited diamond on the surface of chips, and it alleviates hotspots. So you can run your chips hotter.
Yeah. Or you can reduce power. You know, there's ways to reduce power too. Just nobody wants to spend time on it. Anyway,
Yeah,
okay.
It's one of those things. Is it worth doing it or not? And kind of, so this is why you don't want a sort of fixed point for everything. You kind of want to know in a gradient whether you can push something.
Yeah.
That's kind of the information I'm looking for. Is if we can get the gradient, then we can get the job of optimizing it to an AI and do it at a fairly high level.
Yep. Okay. Let's get back to power integrity. We have just a few minutes left. Anything else? Anything about targets? We already have in CDXML min-max voltage. I mean voltage operating, what is it, safe operating conditions, right, for the voltage supply, so we don't have to capture that. Anything that the chiplet vendor needs to require from the integrator. Actually, yes. I have seen a couple of things. One is loop inductance. Right, because when they simulated and also decap for supply, right? When the chiplet was designed, they had to do a little bit of simulation, right? When simulating internally PDN, you have to assume something for the package, right? So they made an assumption that kind of works for them, and they put that as a requirement to the integrator, saying, "Hey, this is what your PDN at the package level should look like if you want us to operate within that," right? That's basically in lieu of providing an entire CPM model and waveforms and things like that, right? They would just require from the integrator to meet those PDN requirements, and if they meet, then they will guarantee the chiplet.
And that is more like the formula-based calculation for sure.
Yeah, because again, it probably depends on the chiplet as well, right? It's a fairly very complex chiplet with lots of currents and switching and things like that. Probably makes sense to provide a lot more detailed data. But for smaller, simpler chiplets that have a single motor operation and they do the same thing over and over, probably just requiring the vendor to meet certain PDN limits should be good enough, right?
There's RF noise as well we haven't considered.
Yeah, okay. I don't want to go there with this right now. My head is already.
Yeah, it's just something, where it's going to spew RF noise. Switch cap
Yeah.
things are bad for noise, and the question then is, where do you put it and how do you isolate it to if something else is sensitive to the noise? So you kind of need noise sensitivity on other chips.
Yeah.
So you can do mitigation.
Yeah.
I like to keep those things. Throw everything in and then throw away the stuff that you can't do anything about later.
Yeah. Okay. Anything else that we would that a vendor will require from the integrator? Anything else comes to mind?
Any material information? I guess that's outside the limits here.
Material information in what way?
I'm just speculating is on what material it was, whether it's RF or whether it's silicon, and then any other special materials being used for either heat thermal management purposes or failure. I'm just thinking at the edge at this point. I mean,
Yeah.
you can leave it out if it does make sense.
Yeah, I'm trying. I'm having a brain whiplash because I was thinking about power integrity and voltages and currents. I'm trying to think about materials in the context of failure, stuff like that. Maybe I think definitely the questions about materials. I think the appropriate place to talk about those is in the MDK meeting. there may be, and what Boone was saying, right, and what Kevin was talking about, the life expectancy, maybe some of those coefficients that are provided, there could be additional level of information that says this is how the life expectancy changes with temperature for any given material. And then if you have a model for the chiplet and you know what materials are in that, you can derate the whole chiplet, right, with temperature and see where you end up.
Right. Right.
Yeah, maybe. That's a good thought. Let me capture it here so that we have it captured. How do we provide information about materials and connect to the reliability and thermal? That's a good question. I don't know the answer.
Okay. Thank you.
I think the MDK meeting is what is it, next week? We can talk about that there. Yeah. Okay. Anything else comes to mind, guys?
Thermal stress.
Okay, that's a different topic. Let's focus on
It
power
came,
integrity.
it came to mind though.
Okay. Okay. Does anything else related to power integrity come to mind, Kevin?
That one came to mind because somebody was doing power electronics for RF and they were doing pulse
Yeah.
stuff and they were getting the thermal stress killed things in a matter of days.
Yes. Okay. If nothing else, let's conclude for today. And we'll continue in a couple of weeks with PI, SIPI. Next week again is a test meeting. So if you're interested, come join us next week again. And the MDK meeting is next week. I think right now, after this meeting is going to be the ADK meeting. So that should be interesting too.
Not ADK meeting pull up 1 hour earlier.
Oh, really? Oh, okay. Oh,
Yeah.
okay.
James has some
then-
conflict, so he put in some 1 hour earlier. Not now, but at least settle 1 hour. I mean, 1 hour before this one.
Oh, okay. Oh, okay. Okay. I didn't. I have missed that email. All right.
Yeah.
Sounds good. Then we'll talk about MDK next week and PI in 2 weeks. Next week is also CDX test meeting. All right, folks. Thank you very much for your time. Thank you for the good discussion. Talk to you next week or in 2 weeks.
Cheers.
All right. Have
Thank
a
you.
good one.
Bye.